Who says, I have two children, at least one of whom is a girl. What is the probability that the man has two girls? The answer is 33 1/3% because there's only one way of having two girls, and the total possible ways of having two children, at least one of whom is a girl, where order is important, is boy, girl, girl, boy, and girl, girl, or three equally likely ways. That is, the probability equals 1 out of 3 equals 33 1/3%. Hence, knowing that the man has at least one girl increases the probability to 33 1/3% from 25% when there's no additional information. Now, consider the following event. You meet a man who says, I have two children, at least one of whom is a girl whose name is Julie. What is the probability that this man has two girls? Now, a number of you will be convinced that we have already given up the game, convinced that the father must have two daughters. If that is what you think our statement of the problem has done, consider the following refinement. Suppose that you are at a party and speak to a man who mentions that he has two children. Before you can say anything, the host of the party rushes him away to meet someone arriving at the door. The man talks to the new arrival for a moment, and you overhear him say, You have two children too? Actually, I was late because one of my children, Julie, is sick today. The probability of two girls in this case, we are told, is now 50%, and this is the paradox. How can adding the name of a daughter increase the probability of the father having two daughters from 33 1/3% to 50%? How can adding the name to the information that the father has at least one girl increase the probability 16.7 percentage points? Perhaps putting it this way makes it sound less surprising. Maybe if we actually demonstrate more clearly how the name information is informing the calculations, the mystery will disappear entirely. To start down this road, let's compute the probability according to the approach just employed in our initial example, which is how it was computed in the book version, by the way, to see what we can discover. Let G sub j represent the girl named Julie, and G sub a represent a girl with any other name. Then the number of ways to have two girls, one of whom is named Julie, is G sub j, G sub a, and of course G sub a, G sub j, or two equally likely ways. The total number of ways is B G sub j, G sub j b, G sub j, G sub a, and G sub a, G sub j, or four equally likely ways. So the probability of two girls is 2 divided by 4, or 1/2, and we'll call this the original solution. Notice that in the original solution we have a number of selections of girls and boys that seem to be with replacement. Of course, this is an important hidden assumption, and one of the first assumptions that is, strictly speaking, incorrect. And the second important and strictly incorrect assumption is that these probabilities are equally likely. Maybe these false assumptions explain something, or maybe not. We'll see. To make our contribution to this problem, we will also make several assumptions, which I will now enumerate. The sample space is the set of all two-sibling pairs of people, where each pair consists of a girl named Julie and either a boy or another girl not named Julie. The girls are selected as individuals, but the same name cannot appear twice in the two-sibling pair. The boys are selected at random, but again, the boys cannot be selected twice. The same boy cannot be selected twice. The girls' names are assigned uniformly and at random. let's assume that there are m girls' names, G1 through Gm, and cap n total girls. One of these G's represents a girl named Julie, and we will call it G sub j. There are approximately as many boys and girls in our everyday population, the one we would like to model, so the total population in our model would be 2 cap n children. Now we can create a tree of probabilities, but we don't need the entire tree, just the portions that have G sub j in them. The probabilities are the probability of B first and G sub j second is cap n over 2 cap n, because there are half of the children are boys, and there are in other words, there are n boys, and cap n times cap n over little m, which is the number of girls that have the name Julie, divided by 2 cap n minus 1, because we've already selected the boy. And that total equals cap n divided by the quantity 2m times 2 cap n minus 1. All right, selecting the other way, Julie first and then the boy, G sub j b, you end up with the probability 1 over the quantity 2 times the quantity 2m minus 1. Notice it's not the same as the one we just did. That's because we're doing it without replacement. On the other hand, if you look at the probability of G sub a, G sub j, you will see that the probability is the quantity m minus 1 divided by the quantity 2m times the quantity 2m minus 1. And you will see that if you do it the other way, probability of G sub j, G sub a, you'll get the same probability. And as I said, the value cap n over m gives us the number of girls having each name. We subtract that value at points because no name can appear twice in the pair. This is consequence of not permitting duplicate girls' names. So the probability is the sum of these, which is 8m cap n minus 5 cap n minus 3m plus 2 divided by the quantity 2m times the quantity 2m minus 1 times the quantity 2 cap n minus 1. That's equation 6. To get the probability of 2 girls, given that we have G sub j, we must normalize the unconditioned probability of having 2 girls, of which one was G sub j, by these probabilities. That unconditioned probability is just the last 2 expressions added together. So we have the expression, the quantity m minus 1 over the quantity m times the quantity 2m minus 1 multiplied by the inverse of the total probability from the last page, and that equals 2 times the quantity 2 cap n minus 1 times the quantity m minus 1, all divided by the quantity 8m cap n minus 5 cap n minus 3m plus 2. Here we let cap n approach infinity and get 4 times the quantity m minus 1 divided by the quantity 8m minus 5 for the probability of getting 2 girls, given that one of the girls is named Julie. Again, if we let m approach infinity, the probability approaches 1/2. We are able to take the limits sequentially in the general case since the limit does exist. We have a restriction to place on m that will make the existence of the limit in that case very clear. I will go into that in a moment. Note, the reason we normalize is that the sum of our probabilities for the branches containing g sub j above does not equal 100%. We must bring the probability for the case that one of the siblings is a girl named Julie up to 100% so that it represents the entire event. To do so, we must multiply by its inverse, and if we do that to the total probability for the event, then we must do so also for the component probability that there are two girls of which one is g sub j.